Okay, our next speaker is Professor Shayegan from Princeton. Okay, can you hear us? Oh, yeah, perfect. Yes. All right. Thank you. Thank you for that. Professor Shayegan received his PhD in electrical engineering and computer science from MIT, and since '85 has been a faculty member at Princeton University, where he teaches physics and electrical engineering courses. His research is in solid-state physics with an emphasis on semiconductor structures and collective phenomena. Has won numerous awards, and he's an elected fellow of the American Physical Society. So with this, Dr. Shayegan, could you please put your presentation, your slide in presentation mode?
I think I did. Can you hear me? I think it's in presentation mode. You cannot see my screen?
It's small.
Small.
You're sharing the wrong screen. Hey,
Okay, now we are there.
Yeah, but if I go on the presentation mode, that's what you have. Yeah, that doesn't show full screen?
Sure.
Maybe on the top you can choose.
Go back to the old one. Yeah, that's one of these slideshow.
This is the slideshow.
Stay there.
Maybe, give me 1 second. Maybe I can share my whole screen. That may be better. Okay. Is that better?
Yes, yes, perfect. Thank you.
Okay. Yes,
Okay.
well, yes.
Go ahead.
Thank you very much for the introduction. And I added this engineering into the title because I'm afraid that's the only time you will hear engineering of quantum computers in my talk. It's mostly physics, but what we are trying to do, in fact, is to engineer specific states of matter, condensed matter, which have uses for topological quantum computing. So we don't have anything to sell even for $30 million. You have to wait for that. So the non-Abelian states, why are these interesting, and this topological quantum computing? One of the main obstacles in building a quantum computer is decoherence or error. And this is because superposition is used and quantum information is essentially encoded in phase relations. So interactions with the outside world can destroy the information, whether it's spin qubits or other types of qubits. So one possibility is to use or encode the information non-locally in a topologically protected quantum state. And let me tell you what that means. So it turns out if you look at the exchange of two particles, for example, I'm showing you on the right side, say blue particle and the red particle, and these are identical. And the z-axis is time. So we are moving two particles around so that at time t1, they are interchanged. So it turns out if these particles are so-called abelian, examples are bosons. For example, boson, the wave function goes back to itself. The final state and initial state are the same if they're bosons. If they're fermions, then you get a wave function which is different by a negative side. So the magnitude squared is the same, but there is a 180-degree phase shift. So it turns out there are these strange particles, not quite proven to exist yet in physics, but there is plenty of evidence theoretically that they should exist, so-called non-Abelian. So when you interchange two of them, the final and initial wave functions are not related by a simple number. You know, there is like a matrix, if you wish, that relates them. So this has consequences, major consequences. It turns out if you braid these non-abelian quasi-particles, you can encode information. So here is an example. You see on the left, again, there's the two particles. And as a function of time, we are exchanging red and blue, and then we are going back at time t2 to blue and red at the original location. So this is essentially the same, t2 is the same as t0. And then on the right side, this is also exchanging, doing the same operation, if you wish. But if you pay close attention to these timelines, imagine you attach a string to these particles and take them around. There is a difference between the two paths. You notice the one on the left side, if you pull up the top plate from the bottom plate, the red and blue strings essentially go parallel. They're not braided. But the right side, the way the timelines are working, the particles are braided, or these non-abelian particles have been braided. So it turns out you can use this to do quantum computing. The original paper came over 20 years ago by Kitaev. There are many other papers, and I refer you to this paper by Chetan Nayak and company in 2008. These are all theory. There is some experimental evidence. I'm not going to go over that there are such particles in two-dimensional systems in gallium arsenide. Those are these two papers. What the focus of my talk is that in our experiments very recently, we have found states similar to these that are much more robust than what has been seen before. So let's get to the physics of these. So it turns out it's crucial for these states. The interaction essentially is crucial for the states. And to appreciate it, I show this simple slide on the left side. Imagine you have a two-dimensional system of electrons. These are the positions of the electrons that are shown here. And on the right side, I'm showing the energy level structure. It turns out even at t equal to 0, you have to fill these up because they're fermions to go to higher and higher energy levels. And so you have finite Fermi energy, which could actually be quite high depending on your density. So it turns out the kinetic energy of the system, which goes as the Fermi energy in a 2D system, that goes as the density of the electrons, and that goes as the 1 over r squared, where r is the average inter-electron spacing. And I'm assuming we're at very, very low temperatures. So the thermal energy is not there. So we have still some kinetic energy. And now we have also Coulomb energy, which is E squared over R. So that goes as 1 over R. And for these states to exist, it turns out you need very strong or large ratios of the Coulomb energy to the kinetic energy. And this ratio, you notice, goes as R. It's a little unusual because R, the bigger R, that means more dilute system. And indeed, when you think of it, a 2D system or 3D system, more dilute makes it more interacting because the kinetic energy drops faster than the Coulomb energy as you go to large R's. But the other energy which is relevant, let's just call it disorder. Ideally, you want these electrons to be free in this two-dimensional plane, but if there are impurities, defects, that's not good. That breaks up the interaction and these states. So that is why one needs to go to very pure systems. So here is the outline of my talk. I'll talk about molecular beam epitaxy and the samples, the recent breakthrough we have had in making the best samples essentially in the world. And these are now showing unusual new states. To understand the data, I'd like to tell you a little bit about quantum Hall effect, fractional, especially the quantum Hall effect, the even-denominator fractional quantum Hall effect. These are the states that have been believed or are believed to be non-abelian. These are in the n equal to 1 Landau level. This all becomes clear in a few slides. The new states that we are observing, in fact, are in the n equal to 0 Landau level, in the lowest Landau level. And now we are seeing a whole number of these even denominator states, fractional filling even denominator. And the one particular one I'd like to focus on is this last item, the 1/2 fractional quantum Hall effect in wide quantum wells. And you will see that these are by far stronger than the traditional state that is believed to be non-abelian. So these are all 2D systems. The platforms for 2D electron systems, of course, are many. The young people are probably most familiar with graphene because that's very popular and busy. But it turns out traditionally either say silicon MOSFET, it's a two-dimensional system, or gallium arsenide, aluminum gallium arsenide quantum wells, where you sandwich the gallium arsenide layer in this blue region. Affords a very good 2D system, or electrons on liquid helium. That's another 2D system. So the one we are focusing on, of course, is this upper right. So how do we do this? If you grow different material on top of another, for example, you start with aluminum gallium arsenide, then you switch to gallium arsenide and back to aluminum gallium arsenide. The way the conduction bands align is shown on top of this. This top line is a conduction band. So gallium arsenide is effectively a quantum well. It has a lower energy here. So you could trap electrons into this layer, and then you form a two-dimensional electron system as shown by this wave function or charge distribution. So the key thing is the material as a whole is neutral. So wherever the electrons come, they leave behind positive ions, as I show you here. And it's very important that you get as clean a 2D electron system here as possible. And what that means is you could put these dopants far away and also make sure that the material that you grow is very pure. So it turns out the big breakthrough that we have made past couple of years is essentially making this material extremely pure as we grow it with molecular beam epitaxy to reduce the residual impurities. So MBE, molecular beam epitaxy, it's essentially an evaporation chamber, evaporator. The key thing is you have different materials, gallium, arsenic, aluminum, and so on, in little ovens. You heat them up and you evaporate on top of a wafer, this crystal. And each of these has a little shutter you open and close to deposit whatever you'd like. So it turns out this is very straightforward. And of course, it has been around for over 40 years. The key thing is to have the system as clean as possible. That means vacuum has to be very low. So the typical pressure we can get now in these systems is 10 to the minus 12 torr. Just to remind you, that means 10 to the minus 15 atmosphere. So it's quite a good vacuum. It's comparable to part of free space, essentially. So I'll tell you in a minute how one achieves that. But once you do that, then you could grow these atomically precise layers. That gives you control over composition, the material, and essentially energy band engineering, which is what we are doing in these experiments. So it turns out about 15 years ago, 14 years ago, Lauren Pfeiffer came to Princeton from Bell Labs. He's an expert in MBE, and in our lab, we also had MBE for many years, 25 years or so. So we combined efforts. And the new chamber, which you can see a sketch of, is rather unique in the world. It is unique in the world in the sense that it has the highest pumping speed, pumping capacity. The whole thing is roughly a pump. You know, there are huge pumps that get the pressure down. There are other innovations that go in it, but also purification of the material is crucial, aluminum and gallium. So the net result is after 13, 14 years of effort, now the system is producing record mobility, record high mobility samples. It's around 60 million centimeters square per volt second. So this number may not mean much to you. Think about the mean free path at low temperatures where we're doing these experiments is around 0.2 millimeters. So that's literally macroscopic. That's how far the electrons go before they scatter off of impurities. So the key thing here is to reduce the residual impurities by making the vacuum better and also the purification of the material. And that is because when you look at the structure of one of these samples, so these are all the little details that go in it. But the electrons are here in this layer. These are the dopants, and the rest is the aluminum gallium arsenide and gallium arsenide. The important thing is, as we are growing this layer by layer, atomically layer by atomically layer, impurities can get in if the vacuum is not perfect or sources are not perfectly pure. And what is happened now in this chamber is that we can grow layer by layer material with less than 1 per 10 to the 10 impurity. So essentially, say oxygen, which is or carbon, which is a typical impurity, there is 1 carbon for every 10 to the 10 gallium, arsenic, aluminum oxide. When you think of it, that's amazing. It's like population of the Earth, which is 10 to the 10. So we have 1 bad guy in this whole system, 1 per 10 to the 10. And we are growing this layer by layer, imagine atomically layer. So some of the details are here. And the most important thing for us is that exciting new physics is emerging, as I will show you here. So next, I'm going to quickly review this quantum Hall effect. Besides getting the systems dilute, you can also add a magnetic field, perpendicular magnetic field to the 2D plane that's shown here. And what that does is it makes the electrons go in cyclotron orbits. The energy is quantized here, as you can see in these delta function. These are the Landau levels. And these Landau levels are very highly degenerate. The degeneracy is a magnetic field divided by h/e. So you can put many electrons in one energy level, and that essentially quenches that kinetic energy that I was talking about before. So that helps bring out these many body states. So here I just show you that's important for later in the talk. These are Landau levels. I'm trying to show the lowest Landau level, ground state, has no nodes in the wave function. Next one has 1 node and 2 nodes, and so on. So these even-denominator states so far had been observed primarily in this n equal to 1 Landau level, and now we are seeing them here. As I'll show you later, you'll see why. So it turns out if you just sweep the magnetic field in one of these 2D systems, you see many ground states. This is, for example, the integer quantum Hall state, fractional quantum Hall state. This is a Wigner crystal state, an ordered array of electrons, composite fermions. So there are many of these. Every few years, a new state comes and gets all the excitement back. The ones that I'm going to talk about are essentially these fractional quantum Hall states and the composite fermion in the next couple of slides. So the integer quantum Hall effect, this was discovered in 1980 and got the Nobel Prize in Physics in 1985. The experiment is very simple. You just pass a current through one of these 2D systems, you put contacts, and you measure the voltage along the the current or perpendicular, so-called Hall voltage, Vxy. And from those, you can get resistances, longitudinal resistance and transverse resistance. And if you plot these as a function of field, you see the following. For example, the Hall resistance, you notice instead of being a straight line, which is what Hall would have predicted a couple of 100 years ago, it has plateaus. It reaches very precise plateaus in units of h/e squared. That's why it's called the quantum Hall effect. And resistance goes through zeros. Whenever this becomes a plateau, Rxx is literally zero, very, very close to zero. So that's the integer quantum Hall effect, and the physics of it, you can understand if you think about the Landau levels. What happens is whenever the quantum Hall is occurring, the Fermi energy is between two Landau levels. There are no extended states, no carrying electrons, and that's what causes the resistivity and conductivity go to zero, and Hall become quantized. So that's pretty well understood as a single particle problem. But now imagine you keep going to higher and higher fields, so fewer Landau levels are occupied. So eventually your Fermi energy, the way to the right, it gets into the lowest Landau level, the bottom one. These, by the way, I'm showing with some width because of disorder. There is always a little bit of disorder in these samples. So then came fractional quantum Hall effect. This was discovered in 1982 and got the Nobel Prize in 1998. And phenomenologically, it looks like the integer quantum Hall state, but now it's when the last Landau level is fractionally occupied. So this trace here shows, for example, 1, 2, 3 with these plateaus. That's the integer quantum Hall. Now to the right of this nu equal to 1, we are in the lowest Landau level, and you notice there are more of these quantum Hall states. For example, this one at 1/3 filling, when the last Landau level is only 1/3 filled. So it turns out the origin of this is pure many-body. It's an interacting state. The wave function is written here. This is pairs of particles avoid each other. And Laughlin, who wrote this wave function first, got a piece of the Nobel Prize. So it's a very special state, a new state of matter, if you wish. And what you notice now is that there are more states, 2/5, 3/7, 4/9. So there are many other fractions at which the fractional quantum Hall state observed. So to understand it, one simple way is to map these states to the integer quantum Hall states through the composite fermion theory. So this is another magic trick that the theorists play. So here are the electrons. At 1/2 filling, there are one electron per every 2 flux quanta. So you attach the flux quanta to the electron, and that magically this gets rid of the magnetic, that gets rid of the magnetic field. And these new particles now behave as if they are at 0 magnetic field because the flux is gone. And in fact, they don't even interact often. So then fractional quantum Hall effect of electrons maps into the integer quantum Hall effect of non-interacting composite fermions. You can see the similarity. If you go from 0 magnetic field here, which is now shifted to 1/2 position, this looks like this qualitatively. So that's a typical explanation. I'm going to go one more slide on this because this is related to what we observed later. So again, we are in the lowest Landau level. It's half field. You have 2 fluxes per electron. You combine them, you get these composite fermions. Now for these, essentially the flux is 1/nu minus 2 because you have attached these 2 fluxes. So you get a new flux for composite fermions, and you can do this simple mapping by just solving this equation. So you can see at the bottom here, the quantum Hall states at fillings 1/3, 2/5, 3/7, and so on, map to composite fermion integer quantum Hall states at 1, 2, 3 integer quantum Hall states of composite fermion. So you can explain this. One thing you notice here is these are all at odd denominators, 3, 5, 7. There is no quantum Hall state at 1/2. This is just a smooth minimum. You also notice the strength of these becomes weaker and weaker, like 2/5 is weaker than 1/3, 3/7 is weaker, and so on as you come towards 1/2. Again, that's important for when we discuss the data. So this sequence is called the Jane sequence from 1/3, 2/5, 3/7 on both sides. That's the expression for it. And this theory essentially explains all the odd denominator, or almost all the odd denominator fractional quantum Hall states in this n equal to n equal to 0 Landau level. But as I said, there is nothing at 1/2. There is no quantum Hall state here. But it turns out, if you look carefully, in very high quality samples, there is another quantum Hall state in the 1 equal to 1 Landau level. And this is the 5/2 states, the celebrated 5/2. You can see there is a minimum here. And if you look carefully, this was observed first in 1987, but later on with better samples, it's clear that the resistance goes to 0. Hall plateau is here. So this is very different. And you notice it's an even denominator, not odd, just like the other ones. So to understand it, this is one possibility, but it's pretty much generally believed that this is what is happening. So we are in the n equal to 1 Landau level here. These two are occupied, spin up and spin down. So once you do the flux attachment, you get the composite fermions as shown here. If these were non-interacting, you would not see this 5/2 state, but it turns out composite fermions have some residual interaction that could lead to a pairing of composite fermions, and that leads to this fractional quantum Hall state at 5/2. The physics of it, or this why they interact and the pairing, is that in the n equal to 1 Landau level, there is a node in the wave function. So that helps the composite fermions, or allows them to come closer to each other and form a paired state. So this paired state is the Pfaffian, or the non-Abelian fractional quantum Hall effect. So there's plenty of theory generally believed that it is so. And as I said, there is some experimental evidence that this state is safe. The problem is that it's quite weak. You can see 4 millikelvin is what is needed, for example, in this sample to see the state clearly. So it turns out, now I'll come to the main part of the talk. In the past few years in our lab, with this improvement in the quality, now we are seeing a whole bunch of even-denominator fractional quantum Hall states in the n equal to 0 Landau level, in the lowest Landau level. 1/2, 3/4, these are some of the ones that we see in different systems. Electrons, holes, wide quantum wells, and so on. So these are some of the references on the right side from our group. So the first question is why? Why are they all showing? All of a sudden, we are seeing these amazing states. The first part of the answer is that the exceptional quality, purity of these samples. But the physics also has to do with finite layer thickness, Landau level mixing. I'll talk about that in the next slide. And this is the physics. So if you're interested in knowing where the physics of these new states come from, is from these two levels. So if you have an ideal to the electron system, you have infinite separation between the Landau levels. So when you're in the lowest Landau level, you can focus on this n equal to 0, make your ground state wave function and so on from this level. It turns out in the systems that we are looking at, the Coulomb interaction between the electrons E squared over R, essentially, E squared magnetic length, is bigger, much bigger than the H bar omega C. So that mixes in the higher Landau levels into the lowest level, and that has a profound effect on these even-denominator states. The other thing that happens is this finite layer thickness. So here is a magnetic field in the z direction. This is the charge distribution of the electrons, say, in the quantum well. And what happens is, if this is thick compared to the magnetic length, to the size of the orbit, that means that the electrons are spread essentially along the z direction. They're not the ideal to the system, and that helps them again come closer together and produces this attractive interaction between the composite fermions. So these lead to the pairing, which happens strictly in the n equal to 1 before. Now we can get it in these states in the lowest Landau level. Okay, so now I'm going to talk about the data, but it's a lot of data. So, and I know it's late, and time is short, so I'm going to skip this one for the holes. I'm just going to focus on the second part, which is observation of these daughter states of the 1/2 fractional quantum Hall state in wide wells. So it turns out if you put electrons in a quantum well and you put a lot of them, they form a bilayer-like charge distribution. The reason is they repel each other from the middle of the well. And so if you put enough, you start to get this bilayer like charge distribution. So many years ago in my group, 30 years ago, we saw that in fact, in systems like this, you do get an even denominator state. You notice at 1/2, there is a resistance going to 0 and you have a plateau. So it was a complete surprise. And the question has been or was for 30 years, what is the origin of this? Is it something special, or how do you describe it? So just to show you, this is 30 years ago. This slide is from one of these new samples. So you can see a very strong 1/2 even denominator surrounded by many of these daughter or Jane sequence states that I was talking about, the ones that we do understand at odd denominator. So this data and our paper, by the way, just came out in Nature Physics earlier this week, if you're interested. Just to show you, the sample is very special. You know, this charge distribution is bilayer-like. This is 72.5 nanometer wide quantum well. Same density in a 50 nanometer quantum well. Data looks very similar, except that there is no 1/2 fractional quantum Hall state. So it is very important that we have the right width and the right density and so on. And that's what I mean by engineering these states. So this is a busy slide, if you wish, but the message I'm trying to get across here is that for 30 years, it was never clear, are the states that we see this 1/2 state, is it a Pfaffian, this one component state that many theorists have predicted, or is it something else? Competitive is this two component, Halperin Laughlin state, which essentially is like two layers in parallel with some interlayer interaction. So the tunneling is zero. In fact, in this case, tunneling, you would like negligible tunneling. Here you want larger tunneling. But it was never clear which one is dominant. So the new data I'll show you now, we have a sample. This is 72.5 nanometers wide. And with the front gate and a back gate, we can change the density, put more electrons or fewer electrons. And as a function of density, you can see here the wave function can be made from a single layer but thick to more and more bilayer, like by just adding electrons. So the evolution of these fractional quantum Hall states are quite remarkable. So this is a low density, 1 × 10⁻11, 1.09 10⁻11. So what you see are these Jane sequence states, 3 7s, 4 9s, and all the way down here. And on the left side, you see the same. Then we go to higher density. Now you can see all of a sudden this 1/2 state come. It's a very nice plateau in the Hall data too. But nothing special here. And then we go a little bit higher. And now all of a sudden, you know, this state shows up here. The strength of this minimum, as you can judge, is stronger than the strength of the minima to its right. So it kind of cuts in the line, you know, becomes much stronger. It's much stronger than the ones on the right. So that gets stronger and stronger. And at higher density, another state starts to come on the left. You notice here, this now becomes stronger than the one to the left of it, the one at lower fields, and gets quite strong. So two special states, one at 8/17 and one at 7/13 filling, start to show up. So what is the significance of these states? So that's just a summary of this, and to show you that there is a real Hall plateau at the correct values at 8/17 and 13ths. So what's the significance of this? So it turns out there is a paper from 2009, theoretical paper, by Levin and Bert Halperin, Harvard, where they actually suggest or predict, if you wish, that if you have a Moore-Reed state, that's that Pfaffian state, you know, the non-Abelian state at 1/2, then the so-called hierarchical states or daughter states are at exactly these fillings, 8/17ths and 7/13ths. So just to put it in a broader perspective, it turns out at 1/2, you could have different states. The Pfaffian, this one here, has these daughter states, 8/17ths and 7/13ths. But like the 2-component, which is abelian or strong pairing, they have different pairs of daughter states. So as you saw, what we see matches exactly what this prediction was. So it turns out when we were waiting for the reviewers, they kept complaining that this paper is not so deeply theoretical, and is there more theoretical evidence? Well, since our paper was put on condensed matter, these 2 papers have appeared a couple of weeks ago, theory papers, and here now 2 different theories, more rigorous. Indeed, they say that 8/17ths and the 7/13ths are descendants of the Moore-Reed or the non-Abelian state. So how much time do I have, Farwood? Couple of minutes?
Yeah, 4 minutes.
4 minutes. Oh, perfect. Yeah. So I just wanted to mention a couple of things. So previous observations of anomalously strong states. So when we saw these in these very high quality samples, we went back to the old samples and we said, did we ever have a hint of these, you know? And indeed, we found some evidence in this 2015 paper that we had, that there are states, we actually didn't pay much attention to them because we couldn't figure out what they are, and they didn't show up in all the samples, but they were there. And then last couple of years, there are several papers, some of them are listed here, in graphene, bilayer graphene rather. They also see 8/17ths and 7/13ths as daughter states in the n equal to 1 Landau level. In graphene, of course, things are a little mixed up, you know, complex. If you wish, there is mixing between the Landau levels, but they see then the n equal to 1 Landau level, 8/17ths and 7/13ths. And in fact, that's one of the main pieces of evidence that in bilayer graphene, these are also non-Abelian. So there's a bit of interest now in the community to use these for topological quantum computing. So to summarize, what we are seeing in these latest class of samples, high quality, are the 8/17ths and 7/13ths. And in fact, we see a phase transition, if you wish, between the Jane states and these states, as we, in this case, raise the density. We see these when 1/2 is the strongest. The other states, the key thing is sample mobility is extremely high, around 10 million, which is very high for these wide quantum wells. And the data suggests that the 1/2 state in the system is indeed non-Abelian, and therefore can be used for topological quantum computing. Now, the key thing here is that the gap we measure, energy gap for, say, the 1/2 here, is around 6 Kelvin. This is about 10 times larger than the gap for 5/2 state. And it's even larger than the largest gaps reported for bilayer graphene. Bilayer graphene, I believe, is around 4 Kelvin. So the gap is very important because the large gap, because this is crucial for error corrections. In that NIAC review paper, they talk about this. So increasing the gap by 10 times is an enormous benefit, has enormous benefits. So the other thing is, you could say, well, bilayer graphene gaps are now big too, around a few Kelvin. But here, I'd like to remind you, our sample size is essentially 20 square millimeter. That's a 4 by 4 or 5 by 5 square millimeter Van der Waals sample. You just put contacts on the four corners and make these measurements. In graphene, the bilayer graphene, the best quality data are in these flakes, which are still of the order of micron size. So the size of our samples is about 10 to the 7 times larger. So that makes it much more interesting for eventually some large for scaling of in a topological quantum computer. The cast, the group I have here, you can see it here. The MBE is done by Lauren Pfeiffer and Kirk Baldwin, and we have help from Roland Winkler for the calculation. So I'm going to just show or leave this here in case there are questions. Thanks.
Thank you. Thank you, Shayegan. We have earned some minutes from the previous talk to ask some questions.
Yeah, good. I try to go fast to help. So are there questions being asked on?
There was one in the back.
Yeah.
One.
Can I turn up the camera?
Maybe you want to come closer.
There's also some Q&A questions.
Yeah, and there are also some Q&A questions, probably also about the previous talk. Yeah, okay, so.
Hi there, can you hear me okay?
Yes.
So I don't know a whole lot about topological qubits. Why is it that non-abelian qubit or non-abelian braids are more useful for quantum computing than abelian?
The reason is this braiding is the key thing.
Mhm.
The abelians, if you braid them, you don't get anything new. So the non-abelian is the key thing for the braiding. And the fact is that, so you see the slide for the braided and non-braided?
I think you're still going back.
You can see my slide?
Yeah.
Yeah, I went back to the slide that has the braided and non-braided. You cannot see it.
Then the next one.
No?
Yeah, there you are.
There you go.
Yeah, okay. Yeah, I guess it was slow. Yeah, so the point is, for example, this braided versus not braided, it doesn't depend on the details of how you do this interchange. As long as these paths are the way I'm trying to draw them here to show that this one is braided, this will have different information, or it will keep the information compared to the one which is on the left. And of course, you have many more particles. You have lots of ratings that you could do. So what you get at the final state, you have the information encoded from that braiding without details of exactly how the paths go. The details of the path don't matter as long as you have some like this. So that's why it's essentially not affected by interactions with the outside world, if you wish. The coherence is kept. That's the main reason. But I know that's not probably the clearest answer. I suggest you have a look at that NIAC paper. They have very nice figures that go over this.
No, that made a lot of sense. Thank you.
Okay. Any other questions?
Any other questions?
Anybody online? Let's see.
Someone raised hand. Yeah, you need to go down, scroll down.
Oh, okay. There are some questions in the chat.
The chat box.
Is there some mathematical number theory favoring some fractions over others?
You mean to make them non-abelian? The even denominator ones are believed to be like this, so they have an advantage, if you wish. I don't know of any odd denominators that do this. So it's crucial that they're at even denominator and that pairing exists. Again, that's a description for these states. Maybe there is some better description. But so I guess all I can tell you is the odd ones, odd denominator ones, are not non-abelian. The even denominator ones could be abelian depending on the detail.
Okay, does that answer your question online? Someone raised their hand. Could you please?
If you look at now, if you look at the participants.
Yeah, I'm looking.
Yeah.
It says George Zipperland asked question, and then the last comment says thank you. I guess he's
No, I
happy.
think, okay, that's
with the
Oh,
answer.
okay.
remove the this website.
Here. No. Oh. Oh.
Oh,
If
question
I may ask a question,
from
is the non-abelian statistics of the dependent states the same as that of the one-half state? Is that are you still getting the same statistics, non-abelian statistics or non-abelian braiding, or is something new?
Just put this just close it and that's it.
it should have the same statistics, and that is why it's so exciting. Of course, experimentally, to prove that it has the non-abelian statistics and therefore good for topological quantum computing, that's very hard to show. So the experimental evidence, I'm showing this slide, maybe you can see it. Bob Willett has done some interferometry experiments on the 5/2 state for many years. For over 10 years, he has been doing this. So it's similar to what I'm sketching here. It's a quantum dot that has finite number of electrons. And the electrons, as they pass through the dot, they can go around. And then they look at the Aronoff-Bohm oscillations, essentially. And from the frequencies and so on, they get information about the braiding and that these are non-abelian. But you can judge for yourself. It's not 100% yet. There is another paper by the Weizmann Institute group, Mori Heiblum. So that's this Nature 2018. So they look at the Hall conductance or thermal conductance of a edge state. And for the 5/2 state, it matches what theory predicts. So that is considered as another reasonably strong piece of evidence that the 5/2 state at least has these properties. For the 1/2 state, that's why I'm hoping we can do experiments in the future. Now that we know it's very strong and it's likely non-abelian, I'm very hopeful that we could do the experiments. We have a collaboration with Modi Heiblum, in fact, to try to measure the thermal Hall conductance, thermal edge conductance, rather.
Okay, one more question.
Can you hear me?
Yes.
So I have more question about the fabrication part. I wanted to ask,
Yes.
you said that there shouldn't be any defects. That's why we go in very low vacuum. I wanted to ask if there is any like characterization or quality check after you have the devices ready, or is that by just like observing the states you will find out that if the device is good enough? How is
Yes.
that process?
Right. Right. So it is indeed difficult, like with SIMS measurements or characterization measurement, to find so few impurities. That's very hard to do. So our estimate, if you wish, is based on the mobility. So there are simple models. If you look at these papers that I list here, I hope you can see it on the screen, or you could send me an email, I can send you. So there are models that relate mobility, or we can calculate the mobility in the 2D electron system. And you'll see the number of impurities. So from mobility value, we know this number, that it is less than 1 per 10 to the 10. Of course, that's just a number, mobility, and it's great to have the world mobility. The key thing is samples are really showing new phenomena, only from these subtle interactions. So I would say it's a combination of mobility and new phenomena that prove to us, at least, that these samples are best quality.
Thank you.
Okay, thank you very much.
Sure.
So,
All right, thank you.
Thank
Thanks
you
for
so
your
much.
attention and all the questions.
Thank you very much.
Thanks, Farber.
Thank you. Thank you.
Thanks.
So